Hi, I'm Kristen Grauman. I'll be talking about computer vision for fashion, and we'll be looking at ideas for creating recommendations as well as understanding how trends are moving around the world over time. Now, fashion is not just about shopping or dressing to impress. Fashion is really about people. And through clothing, we can get direct signals about events in culture, politics, economics. And these are the kind of things that make working in vision for clothing exciting. To paint that kind of picture, thinking about fashion in our politics and economics, think about this timeline where after World War I, there was a preference for comfort and simplicity in the clothing. And then with increasingly the ability to manufacture fabrics, there were inexpensive ways to create looks like you see here. Moving towards and during World War II, where there was a return to austerity in the clothing as a reflection of current events and less about the glamorous looks. And then there's events throughout time in politics. For example, feminism, bringing in the more common wearing of jeans for women, to the anti-war movement with the looks from the hippie look that you see here, and then all the way, say, into the 80s, where women were increasingly in the workplace, and so new looks were emerging, representative of that. So you can see that there's much interest in understanding how people dress, how it changes over time, and it says more than might immediately meet the eye. Meanwhile, there's, of course, quite a bit of exciting applications today with what we can do in computer vision to make styles and products more searchable and accessible, as well as eventually new tools for allowing new design and creativity assisted by AI. Now, there are traditional challenges in computer vision that you'll find in fashion, in the fashion realm, but there's also new ones. For example, it's not enough for us to recognize that these are shoes and move on. In this space of work, we need to be able to recognize very subtle distinctions that make them different. There's also tasks in vision for composition and compatibility that come into play. We no longer want to know only are these things the same or similar. We want to know, do they complement one another visually? And finally, there's issues of personalization and taste that are quite interesting to look at from a computational point of view. So in general, looking at these kind of problems, we're interested in building computational models for style and fashionability. And in the talk today, I'll be sharing some of our latest work about how we can learn about style from web photos, and including try to do so in a way that requires very light supervision. Okay, so a common undercurrent for this work I'll show is being able to learn from the bottom up, where images of people and clothing is the signal we need to start to understand fashion. And there's two main elements of the talk. One is about recommendation, and there's two things I want to show you there. One is this question of how to tweak an outfit to make it just a bit more fashionable. And the other is to look at the first model, to our knowledge, to be able to represent human body shape in terms of recommendation of flattering clothing. Okay, so after talking about recommendation, which is really about an individual's need for clothing, then I'll move to the world stage and talk about style trends and how they're propagating over time. Okay, so here we go. Let's start by looking at recommendation. Now here, this is not recommendation in the sense that here's an outfit that our system thinks would be good for you. Instead, we're casting this as a slightly different problem of editing an outfit. And just to motivate that, we can look to the words of Coco Chanel, who has said, "Before you leave the house, look in the mirror and take one thing off," as a useful piece of fashion advice. So in that spirit of a small change potentially making a big difference to the look, we've been exploring this problem of minimal edits for outfit improvement. So the idea we have is to be able to take images like the left image in each of these three pairs and create the image and look on the right, where this is not a total transformation of the entire outfit, but it's some small change that would make it just a bit better. For example, adding or subtracting one of the garments, or tucking in the shirt, or blousing out the shirt. So if we can do this, then we'll be able to have a system that can look at the thing you've just chosen to wear and tell you the small change, for example, a change to the shirt, that would make it just a bit better. And we call this idea for our approach Fashion Plus Plus because we're looking for those incremental changes in the outfits that indeed make better. So let me just say a little bit about how this works. Our underlying approach is an image generation pipeline. And so we're factoring this representation of an input image on the left into its regions of the garments, so shirt, outerwear, pants, and so on. And for each of those, we're factoring out both its texture and shape. So here on the top, we're showing texture encodings, on the bottom, shape encodings, and you'll see the masks in the bottom left leading to shape encodings for each of those regions. So those will be the inputs. So we'll have encoders learned on the left-hand side. And then there's going to be the Fashion Plus Plus engine in the middle, F++, that is going to alter those latent codes in a direction in which fashionability is increased, and then decode from those updated codes, T++ and S++, into ultimately a reconstructed image that is the improved outfit. Now, to build this pipeline, one important question is how to train it. Because if you think about it, supervision is not a given, right? We don't have pairs of images in which someone is wearing similar clothes but looks just slightly better. This doesn't exist. However, we do have an idea for how to bootstrap such training data automatically from web photos. So the way we do this is by starting again with these representations that concatenate these latent codes for the texture and the shape of each region on the body. And for an image that, like this one, that shows a person in their outfit, we'll consider this as a positive. And to create a paired negative for that instance, we bootstrap web photos by finding an outfit that's far in the visual space from that one and swapping in one of its garments for one piece of that latent code. Okay, so we have a real image that's positive, a negative that's slightly altered by drawing a garment from a mismatched outfit, and now you have a pair to train the system. Okay, so with this kind of training data, then we can train a discriminative model for fashionability. So we'll learn from these latent codes the distinction between fashionable instances and unfashionable instances. Then we can use a class activation mapping kind of approach to work backwards from this discriminative classifier to alter the feature to push it in the direction of fashionability. So in this framework then, we have image in and image out, and the image out will be the one that's been altered towards that fashionable direction. And so I'm going to show you some qualitative examples first, where here you're looking at the inputs for 5 different instances, and now I'll show you the Fashion Plus Plus output for a minimal edit. Here's the after, before, and after. And you can see that Fashion Plus Plus is suggesting changes that alter different aspects of the clothing, right? From changing a color of one of the garments to exactly how the garment is presented. And furthermore, the second output of this system is to suggest the very garments that would achieve the look that was synthesized. So in these examples then, for example, in the second image, the leggings were proposed, and here's an item from a discrete inventory that visually best matches the look the algorithm proposed. Here's an array of more such examples. Here we're looking at the original, and then as I animate, we look at the old and the new. And so you can see the different kind of changes that can be proposed based on this discriminative fashionability model. And one of the most interesting things we think about this model is this ability to control the factor texture and shape. Because what it means you can do is say we would like changes that only affect the presentation of shape. And that's what you're seeing in these 4 particular examples, where here's the original input, and then here are the outputs proposed by the system that are altering the shape. So for example, look at the one in the third instance where it's suggesting to tuck the shirt in, or on the right where it's suggesting to blouse the shirt out. This is very much in that spirit of a small change that has a big impact on how it looks. Okay, so that was a handful of examples of what comes out of the system. To evaluate it, we were looking along 2 important dimensions. One, we want to know, is fashionability improving? And 2, we want to know, is the amount of change small? So on these plots, we're looking at fashion improvement vertically and amount of change horizontally. And so you'd like your method to be having a smaller amount of change for a high amount of fashionability increase. And on the left, I'm showing you this automatically evaluated from data in terms of the visual feature spaces. On the right, I'm showing you it in terms of a human subject study where people actually evaluated how good the results were from the system. And we're looking against our approach, Fashion++, against a set of baselines that do things like just try to push as much as possible in the fashionability direction, that's blue, or make a random change, or just try to find the most similar item, similar outfit to the input. And in short, what the results we're saying is quite consistent that Fashion++ can best balance improving fashionability but not changing things too much. Now this work we did at Facebook and got a little bit of entertaining press, as this example I'll show you here.
Neural, now that Facebook has developed an AI program that can see people's outfits and photos and suggest changes that would make them more stylish. Okay, great, but you first.
Okay, so I've shown you about tweaking an outfit to make it more fashionable. Now, keeping in this line of how do we recommend clothing based on computational models of style, I want to next show you our new work on selecting clothes that will flatter a given body shape. And this is new work that's being presented at the main conference called VIBE. So to motivate, we know that people come in many shapes and sizes, and we know that this also has a very important impact on how clothing looks. However, current models for these recommendation systems are really thinking about the problem in an absolute way, kind of agnostic to body shape, such that the expectation is one shape fits all. Of course, we know this is not the reality, and people come in these diverse body shapes, and so our goal is to recommend clothing that's sensitive to these differences. So let me show you the problem of trying to do this with existing data. So if you look at existing data sets, for example, deep fashion, there's a natural bias towards certain body shapes, not to mention other factors like race or hair style or ethnicity. But here we're focused on body shape, and we see that there's a tendency for these to be images of fashionista types or celebrities, which have a bias towards, as measured here, the tall and thin. When in reality, people are different sizes, and so part of the effort for this project was to look into data that would have a more diverse sampling of body shape. And I'll talk about that data in just a second. So it consists of images from a catalog called Bird's Nest, where we have both images of the product, like the dress you see here, as well as properties of the person wearing it, like their body measurements, and most importantly, this garment on the catalog is going to be worn by multiple models of different body shapes. And for any given garment, a certain subset of the models are wearing it on the catalog. And so we took at this as a very nice form of supervision for a system that can now learn from the body shapes that were most complementary to the different garments and vice versa. Okay, so how we did this then is we look at all the human models in this catalog, and we could extract their body shapes and then do some clustering in order to find the different kinds of body shapes that are present. So think of each of these as a cluster. Now, within a given cluster and for a given model, she has worn some number of the catalog garments. And so what we say is that this gives us supervision to say, for all the body shapes within a cluster that are similar, they may interchangeably wear the different garments that were worn by models in this catalog within that body shape cluster. So these are positive instances of body clothing compatible pairs. And similarly, between clothing worn by one body shape but not another, we have negative instances of body clothing pairings. From here, then, we build an embedding-based model. And this is an embedding that is able to look at either a piece of clothing or a person's body and map it into a space where we want two things to happen. First objective is that bodies should map close to those garments which would flatter them. And the second objective is that bodies should map close to other similar bodies. So just to flesh that out a bit more, on the clothing side, we have both attributes about the garment from the catalog as well as the image itself. And we use encodings of those attributes and a CNN on the image to get the visual part, the visual aspect of the embedding. And then on the side of the body, we have the measurements, but we also have the image of the model from which we extract 3D body shape parameters using a variant of the simple model, and now have the body mapping on the bottom. So these two embedding functions then are trained to meet the objectives I said earlier, such that when we have new instances of a person or a garment, we can find those people or garments that are compatible. Now, when we evaluated this approach, we were interested in how it does compared to traditional recommendation methods. And these are methods that could still pay attention to the images to learn about, learn a good visual embedding, but following the norm would be agnostic to body shape. So the baselines were things like collaborative filtering based on either body aware or body agnostic representations, as well as the proposed approach, which I'm showing in green. And in short, what these charts are showing is for both a set of dresses on the top and a data set of tops on the bottom, we are able to noticeably improve the accuracy of the recommendations for suitability for body shape. Now that's what the numbers told us there, but we also did a series of user studies, including the one I'm depicting here, where someone would look at the person and decide between two garments which one would flatter their body more. And then we look at their recommendations by human viewers against the ones that our algorithm would produce. And conveniently, it looks like my video is hiding the number on the bottom right. But I'll leave you to the paper from CVPR to see that the AUC for these predictions is indeed higher with our approach. So what do the recommendations look like? Well, for a subject like the one on the left, if we took her picture, got these simple body shape estimates, then we would be able to map this person into the embedding and come up with the top row as very highly suggested garments and the bottom row as not suggested garments. And given her body shape, it seems to be looking for things like V-necks, for cuts that accentuate the curves, and trying to stay away from looks that would be shapeless, as you see on the bottom. For another subject, like this one on the left, who's more petite, you can see that the algorithm prefers garments on the top that have embroidery or high waistlines to add height and volume, whereas not preferring the garments on the bottom. All right, so far I've talked about recommendation, and I showed you two main new ideas. One was Fashion++. This is where we could make small shifts in the outfit such that it would become more fashionable. And two, Vibe, this visual embedding for body-aware body-aware clothing recommendations that will start paying attention to how things will look not on just a hanger or a model, but on a person with a very real body shape. In the remainder of this time, I want to show you our latest work looking at forecasting. And here is where we're transitioning from thinking about clothes to recommend for individuals to thinking about clothing as a worldwide phenomenon that, as we will show here, is a migrating or propagating pattern. So the question is, how do we discover these patterns? Okay. So we know then that fashion styles do influence us, as well as we influence each other. And so at the world stage, we're interested in knowing how does a given style, for example, say this style depicted on the left, travel throughout the world over time. What cities are influencing which other cities? By what time lag? These are the kind of things we want to discover, and we propose that discovering this directly from image data gives us an angle that's not really possible by any other metrics. So in order to know how well we've captured this propagation of style across the world, we ground it in a forecasting problem. And the forecasting problem is to be able to look at the profile of a style over time, meaning how popular is it, how often is it being worn, how often is it being purchased for a period of time, and then forecast that forward, right? And so the key insight we have is that if we understand from the data the influence links between any two cities, for example, New York and Berlin, then if we see the history of the influencer, it will help us predict the future of the influenced entity. So here, for example, if New York was influencing Berlin, maybe had I looked at Berlin's style profile for this style over time alone, I would make a certain prediction in red. But knowing that there's this link between what happens in New York and Berlin for this style, I would be able to make a better forecast, as shown here in the yellow curve. Okay, so in short, we want the influence relationships discovered from image data to allow us to shape our forecasts. Now, to study this, we looked at an existing public data set from Cornell called GeoStyle. And it consists of some 7.7 million Instagram photos from 44 cities across 3 different years. And from that data, we can do some discovery of styles. So here are for each row, and there's 2 columns. In each set of 5 images, you're seeing an example style that was discovered based on clustering, finding a Gaussian mixture model over predicted visual attributes. You can see that a style is not the same garment. It means a garment or look within the same family. So what we're going to do then is take each of those styles and learn a predictive time series model to predict its popularity over time in each location. And the key to our approach then is to do this with the influence model. And the particular influence model we consider is Granger causality. And this says that 2 cities here have a Granger causality relationship, or in other words, A influences B if the history of A helps me predict the future of B better than I could predict B based on its history alone. And so once we discover those pairs of cities that have this Granger causality relationship, we use those discovered ties within this prediction model. So here the model is going to take style trajectories of the popularity of every given style and predict them forward in time. And within this network then, we'll link those inputs, inputs that share this influence relationship from cities to city. For example, if Seoul is influencing Austin, then Seoul's and Austin's predictions will be linked, or vice versa. Furthermore, we integrated a coherence part to this model that says that the forecast across all of these styles with their influence relationships needs to be coherent with the global forecast for the style. So when we look at these predictions then, what we've been able to show is that compared to state-of-the-art methods, as well as an array of kind of simple, naive models for time series, we get lower error in this prediction. Okay, both whether we consider the data seasonally or deseasonalized. And this is exciting because we've discovered the trends of these styles from the image data. Furthermore, we're able to push them forward in time to say, for example, how popular will be style X in London 6 months from now? Now, the other upshot of this work is to know what these influence relationships are. And so we have in this CVPR paper here in the main conference, we have the work I've just described and also a study qualitatively of what was discovered, what's influence. So I'm showing you that just a sample of that here, where, for example, on the left, we can see that Paris is a city for which the data shows strong influence out from Paris to many other cities, so multi-city influencer. And here on the right, then Beijing, which is receiving influence from a certain select set of other places in the world. And summing all these things together, if we look at the net influence for each of these places in the data set of GeoStyle, then we can start to paint with broad strokes a map that says how influential are given parts of the world in terms of how much they propagate their styles to other parts of the world. So for example, here we see from the heat map that some of the redder and redder and oranger parts of the world, including in Asia and Europe, are having highest influence, and to others that are having less. Now, this is, we think, a first stab, an exciting way to look at how to mine for influence from visual data directly. But of course, it comes with a caveat that it's only as good as the data is, and there's certainly going to be biases, implicit biases in these images in terms of who's even uploading photos and who posted to post them online, and such that they make their way into this data. All right, so I'm going to stop here. What I've shown is ways in which our current work is looking at recommendation and worldwide style understanding. And there was 3 main contributions I discussed. One is Fashion++, one is the body-aware recommendations, and the third is this idea for how do styles propagate in the world, and how do we leverage that to do better forecasting. This work is all summarized in the papers that are attached in this presentation, and was done in collaboration with Kimberly Shao and Ziad Al-Halal, as you see here. Thank you.